All right, everyone. So, in this chapter, diffraction and polarization, we're going to continue our investigation of wave optics. In previous chapter, we discussed double slit experiment, where to understand how the experimental result, where we see the instead of two bright spots, we see multiple bright spots, multiple dark spots. In order to describe that, we have to accept the fact that light was a wave, because only waves interfere when they overlap, and they give us constructive and destructive interferences. All right, so we use diffraction to kind of describe that, which is a phenomenon when light goes through some kind of opening. So in this chapter, we're going to continue that investigation, and we're going to try to understand diffraction for not only a double slit but also a single slit, and also use that then to look at some of its application like polarization. All right. So remember, the diffraction is technically not a light unique phenomenon. It's a wave unique phenomenon. That means you can have diffraction for any type of waves. In this example here, you can see that you can have a wave that is moving, and um, you can see that those bright spots are basically the wave fronts, which means they represent the crest of the wave, and so that means this distance is the wavelength. And you can see that then you have an opening. So you have a barrier and there is an opening. So you can see that opening is compatible to the size of the wave. And if that's the case, then the light will spread out when it goes through that opening. And that phenomenon, right, when the wave spreads out to fill the space behind the opening, is known as a diffraction. Okay. So again, diffraction is a clear sign that we're dealing with a wave. Here's like a simulated image. So you can see that as light enters that through the opening, right, it spreads out. Now, obviously, that opening, if it's very large compared to the wavelength of the wave, um, then diffraction pattern is not as noticeable, let's say, as when the opening is very small. So, for example, here you can see that um, you have a very large opening, and the wavelength, which you can see in terms of the this is to be the wavelength, but the opening is much much larger, right? So you can still have the light going through, and there's a little bit of spreading, which you can see sort of like in these regions, but still the light in a way moves straight forward without really spreading like in a previous image that we had. Okay, so this is there's a defined region, the shadow, where there is no wave. So that's why, for example, in this image over here, you can see that those columns, right, basically block the light. So you can see that those are the light going through the opening, but then you see shadows. So in order now for us to be able to um, see a little bit of let's say diffraction pattern, right? So when we look at those, um, we talked about that the opening should be very small. So you can say that when the opening is small, then the light going through the opening spreads out instead of kind of going forward and giving you just a little bit of shadow on the sides. So it spreads out. That means what you get here is it spreads out like that. Okay, and it can one of the things we talked about in the previous chapters, that if it spreads out and there are two openings, then the light can overlap. Okay, but diffraction itself is just you know the phenomenon where wave goes through an opening and spreads out like this, and you can see, right, smaller the opening in terms of, like, let's say, compatible to the wavelength size, more visible the effect of the diffraction is more noticeable. Okay. Now, one of the things we have here in this chapter, we're going to study um, diffraction when the light goes through not a double slit, but a single slit. Okay. So one of the things we have here is before that, let's look at a little bit of also history of a wave optics. So here you can see that when we look at the diffraction pattern, um, in terms of a light going through a single opening, here's an experimental result where we're going to see a very bright central maxima, and then you're going to see a dark fringes, and then kind of like a secondary maximus. Okay, so you can see that it is consistent with um, let's say a double slit experiment result where you see that bright spots and dark spots, right, or bright fringes, dark fringes. So it's just a little bit different when you're considering just the one opening. Okay, so there's a very sort of like dominating a central bright spot. Okay, now here's also another example of a light. So you have a opaque object, which means that it pretty much will block the light. So if the light going through, and like let's say you can think of like let's say light kind of going like this, and then what you have here is there's then the object pretty much blocking the light. So then what you see is that instead of going there and giving us one bright spot, it gives us, a result like that. So diffraction pattern associated with light passing by edge of an object. Okay. And what you see again, you see bright and dark fringes reminiscent of an interference pattern. Okay. All right. So here's a little bit of history. We talked about double slit experiment that was done by Thomas Young in 1801. And that experiment basically um, showed us that light has to be a wave or have some kind of wave properties in order for us to be able to explain the result. Okay, so before that, remember Isaac Newton, uh, he was convinced that light was a particle, um, and he wrote a book obviously on optics, and because it's Isaac Newton, everybody was pretty much accepting his conclusion that the light was a particle until 1801. Thomas Young did this experiment, the double slit experiment. All right, so the double slit experiment uh, very conclusively basically showed that light has to be a wave in order for us to see that pattern, but obviously not everybody was agreeing. It's hard to let go of a let's say something that you learned for decades, and something that was given to you by Isaac Newton, right? But still, eventually there are experiments that were done to prove that light was a wave. So for example, here we're going to talk about how in 1818 in French Academy of Science there was so like a debate where a few people, Simeon Poisson, who was a supporter of ray optics, argued that the light cannot be a wave because if light is a wave, um, which is proposed by Augustine Fresnel, who was another you know natural philosopher slash scientist who did a lot of experiments and you know uh, gave us a lot of theory for the diffraction patterns, right? Um, he basically said that you know if the light is a wave, then one of the things we will see here is, for example, imagine you have a flashlight and you have the light, and then you put some kind of object in front of it, like a coin, quarter or something like that. So then what you will see here is there's a screen, then there will be a shadow, right? Because the coin basically blocks. Okay, but according to Poisson's calculations, if the light was a part, if the light was a wave, then there would be some kind of a central, basically source of light. So that there will be a point, a light point at the center of that shadow. So basically, he said that if it was valid, right, a central bright spot should be absorbed in shadow of a circular object illuminated by a point source of light. Okay, so light arriving at all point around the edge of object would diffract inward into shadow region, which means that, let's say, if you're looking at this to be the coin, right? So behind the coin, on the screen, you will see a shadow that will give you sort of like, let's say, some kind of like a central bright spot, but also, around the edge of the object, it would diffract and gives you, sort of like a shadow region. So here's a bright and dark, and thing like that. Okay. So because center equidistant from all points on the edge, light from all points would interfere constructively there, causing a bright spot. All right. So Poisson basically, you can say, right, consider this possibility to be absurd. Okay. So particles of light would be blocked by objects, and such a bright spot never be absorbed. Okay. Then we have um, Dominique Francois Jean Arago, who was the head of the committee for the competition, and he did an experiment. He did an experiment um, to prove that light indeed was um, a wave. So basically, he did an experiment exactly, to demonstrate what Poisson was arguing is not possible. So his experiment basically showed that indeed there will be a notice, there will be a bright spot if you do an experiment. That's sort of like one of those modern experimental results. So you can see, right, this is um, using a penny to block a light. So what we see here is we see a bright spot, right? So we see a bright spot at the center, and then you see those shadows, right? Just like, Poisson argued, you should observe, but obviously, he said that, you will not be able to observe it. So basically, theory shows that you should be observing, but he hasn't seen that before until Arago did an experiment to show that. So now it's, basically that point pretty much called the Arago spot, or sometimes even known as Poisson spot or Fresnel spot. Here I have actually a video of that. So where you can see that from the side, where the light will be coming from the left side, and you can think like there's an object blocking. So then when the light passes the object, at the center, you will see actually the bright spot. There's the black object being, blocking the light. But as the light goes, you can see how at the center you see a bright spot. Okay, so that's basically the Arago spot. Again, so repeating the same experiment, light coming as a wavefront, then being some of the light being reflected when it hits the object, but then what's going through is then you can see the shadow spot and the Arago spot. Okay, so perfectly demonstrate the wave property of light. All right, so here are some more examples of that. So you can see then what happens when you have a circular disc, exactly what we just looked at, and then you have a razor and a single slit. So one thing we're gonna do here is just we talked about circular disc, razor here is for you an example what you see, and single slit is something that we're gonna now consider in greater detail. What we do here is we assume that each illuminated by a coherent point source of monochromatic light. That means the wavelength of the light doesn't change. That means we don't have like a light that has different wavelengths. So let's say it's either green or blue or yellow or thing like that. So that's kind of like what monochromatic light means. Okay. So then let's look at what we call Fraunhofer diffraction patterns. Okay. So we discussed in great detail the double slit experiment, where the light going through two openings, um, where each, right, so there's a distance d between those slits, and here's a screen. When the light then spreads out like this from each opening, and then you see an interference pattern on the screen. So remember, one of the things we would see here is a bright spot, dark, bright, something like this. Okay. So, and each slit was acting like a point source, right? A light source. But how can you then obtain a pattern of light and dark fringes from a single slit? Okay, so remember, here we have source one, source two, two waves to interfere to give us that pattern. But then here we have just one slit. Okay, so then what causes this pattern that we see? So that's an experimental result of a single slit. So that's incoming wave as it goes through the opening. Then it spreads out because we assume that the opening is compatible to the wavelength of the light. Obviously, we want that to be able to absorb a noticeable diffraction pattern. But then what we see here is um, instead of just a light going through and giving us one bright spot, we see basically that pattern. Okay, so these are known as Fraunhofer diffraction patterns. Okay, and now we're going to look at in terms of how we are able to see a diffraction even if we were dealing with a single slit. All right, so let's think like this. The experimental result clearly shows that there is a central maxima, which we can say that this is, right here when the theta is equals to 0 degrees, right? So the bright fringe absorbed at, theta equals 0. Then what we see here is that another bright, another bright, another bright, another bright, where you can see, right, the screen basically dominated by the uh, a central bright fringe at theta equals 0. But then you have just alternating dark and bright fringes on each side of the central bright fringe. Okay. So a lot of times you would then take that, the central one and talk about the width of the central one like this. All right. So now to explain this, we will look at in terms of light going through an opening that has size A. Okay. So we have a finite width of slits, right? And that size, instead of, we in a double slit, we use D to the lowercase d to describe the distance between the slits. That's from center of one to the center of the other one. But here we have just one slit, and A represents the width of that slit. Okay. And then what we have is we have five waves, like going through, like let's say wave one, two, three, four, and five. Okay. Now, what we can do here is we can assume that the waves are in phase when they come in. Okay, so remember this is using Huygens principle. Each portion of the slit now going to be acting like a source of light waves. Okay, one thing we have then is even right now that we have just one slit, we're going to see here is one thing we can think of here is the different parts of the opening then interferes with one another. Okay, so light from one portion of a slit can interfere with light from another portion. And one of the things we're going to see that the resultant light intensity on viewing screen depends on the direction theta. For now, we can see that they all have this angle theta. And to derive some kind of equation, first we're going to like, let's say, split this into two parts. That means we have a over 2 representing two different portion of the slit. Okay, so divide slit into two halves. What we have is that now all waves are in phase as they leave the slit. Okay, all basically pointing in the same direction. Okay, now one thing we have here is if I consider, for example, wave 1 and wave 3. So as the wave 1 and wave 3 basically propagating forward, I can see that the difference between them is this. That means when they both reach some spot, the extra distance that wave 1 will travel compared to wave 3 will be exactly this distance. Okay. And since this is a over 2 and this theta is same as that theta, then I can say that this distance here is a over 2 sine theta using just the trigonometry, where the a over 2 here is the hypotenuse, and basically we're calculating the opposite of that triangle. Right. That means ray 1 travels further than the ray 3 by amount, which is equal to that path difference, a2 sine theta, where again a is the width of the slit. Okay. Now, if I look at then other rays, for example, 2 and 4, they also have the same thing, same as let's say 3 and 5, right? So if I look at 3 and 5, I can also see that being exactly same distance. Okay. Now, If path length difference exactly half a wavelength, okay, then on the screen, what we'll see here is we will see a dark fringe. Okay, so that means they're going to be a destructive interference if they are exactly half a wavelength apart. Okay, so again, cancellation occurs for any two rays that originate at point separated by half a slit width. And they are right now, you can see, right, they're separated by exactly half a slit. So 1 and 3 exactly half a slit, right? 3 and 5 exactly half a slit. Well, same as 2 and 4 exactly half a slit. Okay, and if they are half a slit, separated by half a slit, then what you will see here is you will see then the diffraction, the destructive interference, and the phase difference between such points are 180 degrees. All right, so then one thing we can say is that the wave from upper half of a slit interfere destructively with the waves from the lower half. Okay, so that means their path length difference, which is a over 2 sine theta, will equals to lambda over 2. Lambda over 2 because this is their path difference, delta r, and it's this path length difference is exactly equals, half a wavelength. Okay, so if then we consider waves and at an angle theta, so for example, if I kind of cancel those two, then I have a sine of theta equals lambda, then dividing both sides by a, then I can get sine of theta equals plus minus lambda over a. This is for the first, let's say destructive interference. Okay, plus minus just describe, let's say, if the wave's going like this compared to if the wave's going like that. Then this will give us minus. Oops. This will give us minus, and then this will give us plus. So if they're going down, you'll get minus. If they're going up, they will give you plus. That's right. So like let's say you can use the symmetry, right, to describe back, up and down relative to the central bright. All right, so we can also do this by dividing into, let's say, four parts, right? So let's say instead of having one half, so you can like divide this by a over 4. So then if you divide by a over 4, still what you will see here is that you will see the dark fringes when they are, uh, half a wavelength apart, right? So now what you have is that they're comparing, let's say, 1/4 sine theta, right? So let's say 1 and 2, 2 and 3, and so on and so forth. So it's equals to plus minus half a wavelength. So then, dividing this, you get 2, rearranging. So then you get sine of theta equals plus minus 2 lambda over 2, lambda over a. Okay, so like let's say what you get here is you can in a way say that this is 1 over there, and now this is 2 over here, and we can continue like that. So we can continue like that. So let's say if I go and do, let's say, divide it even further, right? So I have one half, a, so a divided by, two parts. Then I have three parts. Then I have, let's say, six parts, right? So then I have a over 6 equals plus minus lambda over 2, and then kind of rearrange algebraically, then I get sine of theta equals plus minus 3 times lambda over a. So this will give me then the third, diffraction pattern, and so on and so forth. That means what you see here is you get the sine of theta is proportional to lambda over a, and then you have this 3 here is basically, in a way, gives us the position of the different dark spots. And then the general equation will be sine of theta dark equals then m times lambda over a, where m here is what we see like 1, 2, 3, and so on and so forth. That means it's plus minus 1, plus minus 2, plus minus 3. And again, plus means above the central bright, minus means below the central bright. That means what we're looking at here is equation for the formation of the dark fringes. So this equation gives you the positions on the screen where you have then have, let's say, let's say this is some length L, and then on the screen what you see here is position of the distractive interference. Okay, so then you have a dark fringes formed. Okay, so that means this is the equation, and what we have here is then there is no equation for the bright fringes for the single slit experiment. What we're dealing with here is only dark fringes because we have a very bright central, a maxima, right? A bright fringe. And then all the other maximas are very, very faint. So that means our concentration is on looking at the formation of the dark fringes. All right. And also one important thing to note is that there is no m equals 0 for the dark fringes. In a double slit experiment, you had bright, but then what we had here is you have two dark, and this was m equals 0, this was m equals 0. That was two dark fringes, one above, one below, of this is like, let's say, double slit experiment, where this is basically the central bright. For the single slit experiment, what we have here is there is no m equals 0, right? So when we see the graph, we will see that you basically have, this is the central bright, and then this dark is your first minimum, equals +1, and this one is equals -1. That means what you get here is, you can see, right? Then this is +2, and this is -2, and so on and so forth. That means what you have here is, the central bright is basically acts like a reference position, So then, for example, if you calculate the distance from the central one to the first dark, then you have also the same distance from the other dark below that, and then the distance from one dark above to the next dark below then can technically give you the width of the central one. That means what is the width of the central one is the distance between plus one m equals +1 to m equals -1 dark fringes. Okay, that means if you calculate, the distance for this minimum, so then this theta can be doubled to find then the width, either in theta, in radians, or in degrees, or in meters um, for the central bright. Okay, so again, so this equation, um, so a sine of theta is equals to m times lambda, right? So this will be then for the calculation, um, if I divide by a as well. So this will be the calculation for the dark. So that's why I put like d for the dark. Okay. So remember again, m is equals to +-1 +-2 dot dot dot. Okay. So now, if the theta is relatively small, so let's say the theta here is under 5 degrees, then this equation can be simplified to theta d, because then, sine of theta is approximately theta. So then this will be then m lambda over a. So you can write it like that. So that means, what we have here is we can calculate then that position in terms of angular position. So you can have either theta or, like, let's say, either degrees or radians. Okay. So again, this equation here shows you that, m equals 0 is absent, right? So there's no m equals 0, and the central bright maximum is twice as wide as the secondary maxima. Okay. So one thing we have here is, so you can rewrite this for the small theta when theta is small. So then you can say that theta dark is equals to m times lambda over a. Then similar way, we can say that if this is length L, I can find maybe then the y position of the dark spot, right? I can find the y position of the dark. So for that, I again use y equals L tangent of theta, right? So let's say this is, what, right now we're only dealing with dark, so it doesn't really matter. So let's say m is the order, right? Mode order. So L tangent of theta. But since, theta is approximately sine of theta, approximately tangent of theta, I can also say this is L times theta m. And since theta m is this, I can then relate y of m as um, m lambda L over a. So this is basically finding the linear position. So this here your result will be in degrees. So here your result will be in radians, and here your result will be in, let's say, meters, right? So this is, you get the linear position, and those are how things related. If the angle theta is not small, then you cannot make that, you know, let's say, combination, right? You cannot combine those together. So then you have just two, right? Here's will be the first one, and here's will be the second one. Equation dealing with a single slit. That means if your thetas are large, you basically use those equations. If your thetas are small, and you can pretty much make this calculation in terms of that. So in any case, one thing you can do here, you can just calculate theta, um, basically using this equation over there, and then see if your theta is small or not, if you can make the assumption. But sometimes once you calculate the theta, then you can just plug it into this equation and just use y equals L tangent of theta instead. All right, so those are in a way the only differences that we have for the double slit and single slit. For the double slit, we calculate both dark fringes and bright fringes, and there is m equals 0, 2m equals 0 for the dark fringes. For the single slit, we only calculate the dark fringes, and there is no m equals 0 for the dark fringes, and we don't even bother ever calculating anything about a bright fringe unless you calculating the width of the let's say central bright. So you can also kind of calculate that. All right, so let's look at a few examples. A coherent microwaves or wavelength 5 centimeter and a tall narrow window in a building otherwise essentially opaque to the microwaves. If the window is 36 centimeter wide, what is the distance from the central maximum to the first order minimum along the wall 6.5 meter from the window? All right, so what we can see from here is that we're given wavelength, which is 5 centimeters. We're given that the window is 36 centimeter wide. That means that's our A. And the wall here is 6.5 meter away from us. So that means that's our L. All right, so then what we do here is, as I said, right, so since we don't know if the theta is going to be large or not, so we go ahead and use this equation of sine of theta. So we want to know the first order minimum, which means that, m equals 1. So then sine of theta is equals to m lambda over a. So from here, then we can calculate taking the m equals 1. So I can say that is 1 times 5 centimeters, then divided by 36 centimeters. I don't have to convert to meters because both of them are centimeters, so units cancel out. Okay, so then what we get here is we get 0.139, and then I do inverse sine of 0.139 to solve for theta of 1, 0.139. Then we can get theta 1 to be 7.98 degrees. Okay, so that's basically the um, distance from the central maximum to the first order, um, first order minimum. But here's the thing: when it says distance, it generally means that vertical distance. So we got this, we got theta, but then what we need actually is y1. So which is now has L tangent of theta equation because theta is larger than 5 degrees. So we then put 6.5 meters. That's our L. Then tangent of 7.98 degrees. Then we're going to calculate 91.2 .912. Then you just basically convert it into centimeters. So 91.2 centimeters. That means going from central bright to the let's say first dark, it's going to be almost a meter. That's why when the openings are really large, you don't really see the absorb that diffraction patterns. Right, here's another example. A screen is placed 50 centimeters from a single slit, which is illuminated by with light of wavelength 690 nanometers. If the distance between the first and third minima in the diffraction patterns is 3 millimeters, what is the width of the slit? All right, so in this case, we have screen is placed 50 centimeters, so that's our L. So let's write as 0.5 meters. Um, and a light has a wavelength of 690 nanometers, 690 times 10 to the negative 9 meters. And it says if the distance between the first and the third minima is in the diffraction pattern is 3 millimeters, that means we're basically given the distance, right? Sort of like this delta, delta y between those two. See, the units are in millimeters, so that's the vertical distance. Okay, that means, for example, let's do, let's say here's our opening. So this is A, and let's say here's our screen. So then what we're saying here is that distance L here is 0.5 meters. So what we're gonna here absorb is, here's the central bright, which is very, very bright compared to all the other, the maxima. So then here's the dark, then here's gonna be another dark, and then here's gonna be, let's say, another dark, right? So for example, and then, a little bright here. So this is m equals 1, this is m equals 2, and this is m equals 3. So then this distance, so this distance here is then 3 millimeters. That means the distance, sorry, not this distance between first and third. That means this distance here. So this distance here is then 3 millimeters. Okay. All right. So then, which we can say that, let's say our delta y, right? Delta y, where this is y, 3 minus y1, basically. All right. So from here, what we do is we look at in terms of y equals L tangent of theta. Okay. And y equals L tangent of theta. And then this will be sine of theta equals m lambda over a. Okay. Now, generally, when we're dealing with a small wavelength like that, light going through a small opening, we can assume that thetas are small. So if the thetas are small, so we can say sine of theta is approximately tangent of theta. Okay. So then I can say y over L, which is equals to tangent of theta, is approximately theta, approximately sine of theta. That means it's equals to m lambda over a. Okay, so that means it's equals to m lambda over a. Now we are given that delta y is equals to 3 millimeters, so which means it's 3 times 10 to the negative 3 meters. Okay. And what we have here is, in a way, let's say right now, if I do come back to this equation, let's call this equation 1. So my equation 1, it says y over L. Okay. So that means what I can do here is I can say this is then delta y over L is equals to then delta m times lambda over a. Because what I have here is I have two different order, right? So I have the delta m and delta y, two things that represents those different, fringes. So I can see that my delta m is difference between, third and 1. So 3 minus 1 equals 2. Okay. And delta y here is, given like that, which is 3 millimeters. So then taking equation 1, let's call this then equation 2, because now I'm doing in terms of change. Then I can just rearrange and solve for a. A is equals to delta m lambda times L over delta y. Okay, so then it's equals to then delta m here is just 2 times lambda is 690 times 10 to the negative 9 meters. Then L here is 0.5 meters. Then this is divided by delta y, which is 3 times 10 to the negative 3 meters, which is the 3 millimeters. I do that calculation. So for A, and I'm going to get 2.30 times 10 to the negative 4 meters. That's the calculation then for the A. That means this the width of the slit is roughly 0.23 millimeters. Okay, so that's how we can, again, you can see, right, when the angle is small, we can rearrange and um, solve for position. So that's why when it's asking for the distance, you generally ask to calculate the the linear position, which is going to be sort of like in meters. All right, so next let's look at the uh, intensity of a single slit diffraction patterns. All right, so the analysis for that will show us that intensity will be given with this equation over here, where intensity is equals to the maximum intensity, where the maximum intensity always represents the intensity of the central bright spot, and that always will happen when theta equals 0 degrees. And then what we have, the wavelength, is the wavelength of the light used to illuminate slit. And generally, remember, we're using monochromatic light. That means it's always going to be just one specific wavelength, right? That means one thing we can see from this the diagram over here is that if we plot then the intensity um, in terms of the intensity graph, so you will see that this is for the theta, intensity versus theta. So when theta equals 0, then you get the maximum intensity. That's for the central bright. Okay. Then the first dark one will happen when the theta equals negative pi, or when it equals to pi. That means you get those first dark above and below the central one. And then the second dark will be when the theta equals 2 pi or negative 2 pi. And then you can see, right, 3 pi and so on and so forth. So this graph demonstrates in terms of, like, let's say, what will be the theta, right, for the intensity for the orders of, m equals plus minus 1, plus minus 2, and so on and so forth. So this is basically for the a single slit experiment, intensity for that. So sometimes you can just take a ratio of intensity, or divided by the maximum intensity, and we can see that the graph, the shape of the graph changes significantly when you have n number of slits. So we're going to talk about diffraction, the diffraction grading, when you might have many different slits. But over here, so let's say you have let's say n number of slits. So the first one gives you the n equals 2, which is a double slit experiment. But then you can have, and this is something we looked at in the previous chapter, that we have n equals 3. And you can see, right, when n equals 3, then what you get here, you get not only primary, but you can also get the secondary maximum. Okay, then n equals 4, then you can see again, now you get, two secondary maximum, right? N equals 5, n equals 10. And what we get every time, you have larger, higher the value of the, the slits, the narrower the maximums, right? So, and you can see that they're getting closer and closer to one another. And when you can see for n equals 10, your the maximums are much closer to one another, right? So it's and you can see that more you increase the number of slits, the closer, closer that maximum going to be to one another. That means you basically kind of like not an envelope like that, right? So like a more like a straight line becomes. So that's something we're going to see in a little bit later on when we look at diffraction grading. Okay, so we can also again kind of like analyze the two slit diffraction pattern, and one of the things we can see here is if you look at it sort of like as a whole, right? So instead of maybe like, let's say, looking at this small region of the diffraction, the double slit diffraction pattern. So if you just look at this, and this is what we looked at in the previous chapter, you basically see that the central one is just a slightly brighter than the first order maximum. Like, let's say m equals 0 for the maximum is brighter than m equals plus minus 1, but not by much. Then m equals, plus minus 2 is a little bit fainter, plus minus 3, so on. But, more or less, for this region, right, the intensity decreases, not like, let's say, significantly like we saw for the single slit. But then if you kind of um, look at the combined equation, right, you can see that you can more or less model it as well. This one, just like the a single slit. So what you have, this is, can be considered the entire bright, central bright, right? So that means, this is the central bright, and then this is the secondary bright, and so on and so forth. So you can kind of look at it in terms of this. And then the combined equation will be then, um, so this is the intensity for the double slit diffraction patterns. So pretty much combining those equations for the double slit and the single slit. So you get pretty much this equation. So you have I, which is I max times cosine square. Then you have the argument of the cosine square times the ratio of sine of pi a sine theta over lambda divided by pi a sine theta over lambda quantity squared. Okay, so this again represents single slit diffraction pattern, factor in the square brackets, acting as an envelope for a double, two slit interference pattern, which is a cosine squared factor. All right, so let's look at an example here. Diffraction pattern is formed on a screen 12 centimeter away from a 0.4 millimeter wide slit. Calculate the fractional intensity I over I max at the point on the screen 4.1 millimeter from the center of the principal maximum. All right, so let's then do this calculation. So we're given that a pattern is formed on a screen 120 centimeter away. That's our L, and it's a monochromatic 546.1 nanometer light. That's our wavelength. And we're told that calculate the fractional intensity I over I max at the point on the screen 4.1 millimeter from the center of the principal maximum. That means that basically, we're given our y position, right? So y is equals to 4.1 times 10 to the negative 3 meters. Okay, so obviously then this one will be times 10 to the negative 9 meters, and this one will be then 1.20 meters. Having everything in meters, generally good idea. All right, so here then what we have is the equation. So for a single slit, right, is I equals I max. Then we had sine of pi a sine of theta over lambda over pi a sine of theta over lambda, then the quantity squared. Okay, so that's our equation. But we want the ratio of I over I max. That means, basically divide both sides by I max. Okay, get rid of that. So that means this is what we want. All right, so that means one of the things we want to know here is sort of like, let's say, what is, let's say, sine of theta? Okay, so because that's kind of like, one of the things we want, right? Sine of theta divided by lambda. So if we can calculate that, then we should be able to get that. Okay. By the way, like, let's say in this equation is not sine of theta divided by lambda, but sort of like, let's say the argument is not theta divided by lambda, is the sine of theta divided by lambda. And like, want to make sure that you guys are aware of that. So let's say. Okay. All right, so then this is equals to, okay. So that means we need to know what the sine of theta is. Okay. So we are given L, lambda, and y, and those are in a way good enough for us to find, because again, using the sine of theta, approximately tangent of theta. So I can calculate this. Remember, one equation for sine of theta, was m lambda over a. But I don't know what the value of um, a is at the moment, right? So I don't know what that value is. But um, let's see. Actually, I do have. Sorry, I just noticed that I did not write that down. So a is also given to us, and it's point 4. So basically zero point 0.4 millimeter, or we can just write as 4.0 times 10 to the negative 4 meters. That's also given to us. All right, so either way. So sine of theta equals m lambda over a. Um, but, this is also equals to the tangent of theta, and tangent of theta is equals to y over L. Okay. So, and y over L, so I'm given my y, I'm given the L, and we can just use that. So y is given as 4.1 times 10 to the negative 3 meters, divided by L is given as 1.20 meters. Meters cancel out, so we're going to again calculate 3.417 times 10 to the negative 3. The, just a unitless quantity. That means now I know what my sine of theta is. So then one thing I can do here is inside, right? So you can see that here I have, this one says pi a sine of theta over lambda. And at the bottom, I have then pi a sine of theta over lambda. And remember, I cannot cancel those because, the numerator is an argument of another sine. So that's why I cannot cancel any of those things. But since I have sine of theta, I can say that if I do pi times a sine of theta over lambda, then I can basically calculate those quantities. So I already have sine of theta is equals to that. So then I can say pi times a, and a is 4 times 10 to the negative 4 meters, then times sine of theta, which is 3.417 times 10 to the negative 3, then divided by the wavelength, which is given as 546.1 times 10 to the negative 9 meters. So you can see, right, meters cancel out, and I have just a radiant, which basically exactly what I want. Um, so this is then going to give me 7.8862 radians. Then I can take that and plug it into this equation, because now I have, sine of that argument, which is pi a sine of theta over lambda, which is 7.862 radians, then divided by 7.862 radians, okay, then quantity squared. So if I calculate this, I will get 1.62 times 10 to the negative 2. That means that the ratio here is 1.62 times 10 to the negative 2. And that's my answer for the, you can see, right, the fractional intensity at the point on the screen, 4.1 millimeter from the central. That means it decreased by that much. Okay, remember the intensity at the central one is I max, and if I do I over I max for the central one, right, so I'm going to get 1, but here, I get a decrease in intensity by that much.